All right, so today we have Duncan Wright from the Worcester Polytechnic Institute. He's a postdoc scholar there. He received his PhD in 2019 under the advisement of George Androulakis. He studies commutative and non-commutative probability and their applications to biology and physics. He is presenting joint work today with another recent graduate of UofSC, Robert Vandermolen, and the title is A Graph Theoretic Heuristic Algorithm for Quantum Error Correction. So go ahead and take it over, Duncan.
All right. Well, thanks for the invite. It's nice to see some familiar faces, or at least some familiar names. I know over the internet we don't always get to see faces, but that's part of it. So this work is really kind of at the impetus of Rob, who graduated the year after me under Ballard, and he's basically running the Department of Mathematics at St. Mary of the Woods College. I don't know how he found time to get this, but he invited me to talk about, or to think about this project with him, and so this is what it resulted in. So again, thanks for having me. Anyway, so table of contents, basically broken up into 4 sections here. Project background, I'm going to just kind of look at a highbrow view of just the state of quantum computing and kind of where this work fits in. And then I'll talk about these reflexive stabilizer codes. For those of you that know about CSS codes, there's really not a whole lot of new impressive mathematics here, but the nice thing about it is this connection to graph theory and kind of this new viewpoint that this allows us to have. And that's going to be done in that 3rd section. And then since this is kind of a new way of looking at it, there's all kinds of open questions for future work and maybe collaborations. So hopefully spark some people's interest, and maybe you'll have some new projects to work on. So project background, first, let's just talk about classical versus quantum. So it doesn't really matter how you're thinking about this, whether you're thinking about a transistor running an algorithm on a computer, or talking about communication between Alice and Bob. I kind of just lump these all into one type of viewpoint. Really, it's just, how are we going to implement algorithms and run things on a computer, send information, store information. It's all kind of one big group. So where are we at right now as far as classical versus quantum? Well, if you look at some of the biggest supercomputers, this is kind of one of the big ones where we're getting at here with error correction. Through these passive and active error correction techniques, you can basically get 1 error in every 10 to the 20 operations, which, basically you never have errors as far as actually reading things out. And if we look at that compared to what we have for quantum right now with fidelity, like 99.9% for some of these qubit systems, we're about on the order of 10 to the 4 operations per error. So there's still a long ways to go there. As far as other things that might be of interest, right? Some of these supercomputers have 19 billion transistors, around 10 to the 10 transistors. I'm not really sure how that really compares to qubits in a system, honestly, but if you look at Google's Sycamore machine that they used to show quantum supremacy, that was 53 qubits. And even that was not a system that can do everything you wanted to. It was just to prove a point. And if you look at D-Wave, sure, we got 10 to the 12 qubits, around 5,000, but there's not great coherence there, and it's really for just solving classical optimization problems. So I'm not sure that's really comparable either. And then kind of this last thing we're looking at here is operations per second. So some of these supercomputers around 10 to the 17 floating point operations per second, whereas the best we've gotten with quantum so far is around 10 to the 8. Now, it doesn't mean that they can actually do 10 to the 8 gates per second, because they can't actually do that many gates in a row, but that's around the time scale that they can effectively have these 1 or 2 qubit gates in some of these different situations. And so I guess the key thing here is there's a long ways to go, and we're all making strides to get there. We don't really need to get to the 10 to the 20 operations per error that we have in classical, but to make something commercially available, you really need to be around 10 to the 10 or 10 to the 14 is what I've heard. So there's still a long ways to go there. Okay. So where is the work being done in quantum computing right now? Just building these quantum computers. Well, there's all kinds of different machines, and that's kind of going to be a key point that I'm going to on here. That this wide variety of different machines makes a big difference as to how we're thinking about these things. So in industry, it seems like the main thing people are using, not the only thing, but are these superconducting qubits. For instance, on the left there, you see Google. That's a picture of their Sycamore 53 qubit chip, which is how they did the quantum supremacy. In the middle, that's one of the IBM Qiskit machines. It's got 16 qubits. And Rigetti on the right there, I think they also have some of that cloud-based quantum computing that you can work with, and that's around 20 qubits. So, this is kind of where industry's looking at, but, in academia and all these other things, there's all kinds of other systems like quantum dots. Quantum dots are, I know they're working on them in lots of different areas, and it seems to be one of the more promising of these systems that are working. They're working with like silicon and silicon germanium systems. There's other talks you can listen to where they'll talk about that if you're interested in the material science and the physics. But one thing that's interesting that applies to this talk with these quantum dots is a group at University of Wisconsin with Mark Erickson and Joel Corrigan. They actually recently kind of showed proof of concept of being able to show the difference or to measure the energy difference in transitions from the ground state to any of 5 different excited states, which kind of means that you don't necessarily want to work on a qubit system with these things, but kind of the more general qubit system. And so I think that's interesting for this talk because it means, at least on some level, the qubit system or error correcting that I'm going to be talking about at least has a proof of concept related to it. Other types of things, another industry company, IonQ, they've got some of these systems with trapped ions. You've also got D-Wave with this adiabatic quantum computing. Like I said, they have lots of qubits, but it's only for specific types of problems that they can solve. And then some other ones, there's neutral atoms. There are even more that I couldn't find a cool enough picture for that I didn't include here, such as like quantum spin liquids, topological qubits, nuclear magnetic resonance. But they didn't have cool enough pictures for me to show you here. But kind of the point is that there's a lot of work being done with a lot of different machines and a lot of different methods. And you kind of have to be in the game to play. So there's all this work being done with quantum computers right now. So how are we actually going to close this communication gap? Besides building those computers and making them larger and larger qubits, I mean, there's kind of this whole idea here with this layered architecture of everything that needs to be done, going all the way down to building those machines, that physical structure in layer 1, going up through layer 2 where you've got your basically passive error correction, layer 3 where you've got your active error correction, and that's where this work's going to fit in. And then obviously you're going to need to start coupling it to classical computers because no one thinks that quantum computers are really going to replace classical computers. They're going to be need to use in tandem. And so this is really where we're at, or the steps that need to be taken. And like I said, this work's going to fit into that 3rd layer there. And really, so since this is a huge problem, needs to be work done all around, right? So this middle layer is kind of the biggest focus, I think, right now. I guess the physical qubits as well, but that kind of bleeds into that 2nd layer as well. Really just trying to get some better fidelity for these qubits, so less errors per, or operations per error, or sorry, more operations per error. And you can kind of see over on the left-hand side here, something we're going to be talking about is this difference between logical and physical qubits. Yeah. And just kind of to finish this off, this kind of background section. This is a slide that I basically took from William Oliver. He gave a talk at Frontiers in Quantum Computing conference at URI that was just last month. All of those talks were recorded, so I really encourage everyone to go to that their Frontiers in Quantum Computing website and go find this talk. I think it's in session 9. It does a great job of kind of laying out maybe a bigger, broader picture of where the state of quantum computing is, and then kind of ties it into actually the physical machine that he's working on. But you can see here basically some of these different machines that I've talked about and where they sit as far as their fidelity and their gate speed. So on that x-axis, you can see gate speed, right? Hertz, so cycles per second. That's where I got this 10 to the 8. Over on the right-hand side, you can see that's with like the superconducting qubits on just a 1 qubit gate. And then as you move upwards, you're getting better fidelity, right? So operations per error is on the left side, which is exactly what gate fidelity is. And all the time we're moving up on this graph. And I guess that red line is drawn there really because, well, if you have something below that, that's not really something that you can rely upon for computation. So that's kind of 1 in 100 operations per error. And especially with like surface codes, which is what a lot of the superconducting qubits are being done on, that's kind of where the bar is. All right, so hopefully, even if I didn't need to, I've convinced you that, getting into this area of quantum computing and quantum information science it's an exciting area to be in, lots of work being done. And now I'm just going to go ahead and move on to basically where this work fits in is more of that active error correction. All right, so just kind of putting everything together with what is error correction. Well, the basic idea here is you've got your logical bits or qubits here. What do you want to do? You want to code them into a larger space. That's where our physical system is. And then if we want to actually, if we're worried about errors in the system, well, what's that going to do? That's going to perturb these code words as we send something from Alice to Bob, or as we're doing a calculation or running an algorithm or whatever. And the main idea is we want to make sure that we have enough space here so that whatever the errors are, they're going to keep these subsets separated. So that's kind of just a broad overview picture of what that is. And classically, just a basic example to make sure we're all on the same page here. You can have this 743 Hamming code, and right, this is just with bits. So you're taking 4 bits and encoding it into 7 bits. And what are we trying to protect against? We're trying to protect against bit flips. And sure, this works great. You can see that 3 there basically is the distance. You need 3 bit flips to get from one of these words to another. But what's the problem is that in quantum computing, there's lots of different errors to consider, right? We're not just worried about flips, we're also worried about phase errors and everything else that goes along with that. So let's talk about what those errors are. All right, so as I said before, the math here, I mean, if you know what a CSS code is, you're going to hopefully follow this very easily. We're just going to set it up with these Pauli operator errors. Really, you can just think about X and Z. When we're talking about qubits now, you see that I've got A and B and F sub D. So we're talking about some power of a prime in really any field here. So essentially, these things work exactly as they do on qubits. And as an example, on qubits, it's exactly the Pauli operators. And I guess this Y I kind of just threw in here in the qubit one. Those aren't really considered very often in these qubit examples, but I threw it in just to kind of close that picture with the qubits. Anyway, so if these are what are happening on a single qubit system, then what are we going to do to get an error on our n-qubit system? We're going to take an A and a B in FD to the N. And we're going to tensor these errors to get something of this form DAB. Once we have that, then we're going to have essentially the whole collection of these things. Once we multiply by the pth root of unity, we're going to have a group, which makes things really nice to work with, right? I mean, we all took algebra, and we know the significance of groups. And so what properties make this easy to work with? Well, here's just a few of the properties of DABs that are going to be kind of lying under the hood of the types of things I'm going to be talking about. I'll kind of mention probably the most important one here is the one at the bottom, which tells us essentially that we have this symplectic inner product, which allows us to really talk about how commutative two of these operators are. And importantly, just in general, as a quantum stabilizer code, you're looking for, first of all, you can see there, right? You're looking for a commutative subgroup. So we need that commutative subgroup. And really what that's going to allow us to do, since we're looking for a joint eigenspace, well, we know that if they're commutative, they have this same decomposition into their eigenprojections, right? So that's going to allow us to find that joint eigenspace of operators. And due to that symplectic inner product, we can see that these things are commutative exactly when that symplectic inner product is 0. So that's really what that gives us there. All right, so just an example I'm going to go through here is with a short code. And this kind of really gets at the viewpoint that a lot of these error correcting codes are taken at this point, right? It's very much a classical viewpoint where we're like, okay, we have X errors, we have Z errors. If we have X and Z errors, we're just going to kind of stack those things on top of each other and then figure out maybe from there what types of errors we might correct. So basically, what can you say in this case? Well, if you want to protect against flip errors, you can kind of do this kind of repetition code idea, right? Just take our 0 and our 1. This doesn't break our no cloning theorem because we're still putting it into, I mean, you'd still take an alpha 0 plus beta 1 into alpha 0, 0, 0 plus beta 1, 1, 1. So you're not actually worried about cloning. That doesn't break that. But this will allow you to protect against flip errors. Similarly, if you want to protect against phase errors, you can take the kind of Hadamard basis states that I give there at the bottom, that plus minus, and just triple those as well. And so if we want to protect against flip errors, you do the first one. You want to protect against phase errors, you do the second one. You want to protect against both, you just concatenate them. Right, so you can see what I've done basically here. First, you just go up to the flip error protection, and then this 0s and 1s, exactly what's happening is you're taking, right, this idea here, 0 plus or minus 1, and you're just putting it on each of those individual pieces, right? And then you get that 2 root 2. So this is kind of the way that, at least in my opinion, that you see a lot of these error correcting codes being thought of, is just from a very classical viewpoint. And there's not really a look at what's the machine it's going to be implemented on, and what's the what are the errors that are kind of inherent to those machines. Anyway, so that's just an example of a stabilizer code. So now I'm going to get into what these reflexive stabilizer codes are. So if you look at CSS codes, essentially, they just look at those two separate cases, the X errors and the Z errors. So basically, you're looking at DA0 and D0A, these two different things. These reflexive codes, the reason we're calling them reflexive is, you can see here, is we're building them off of having A both for X and Z. That's kind of where that terminology came from. You can easily see that this is going to be commutative. And so, like we said, we want some joint eigenspaces. So what are we going to do? We're going to take eigenvectors from these different spaces, and we're going to basically make those our code words. And for example, you don't have to take a shot in the dark. It's really fairly simple to actually calculate what these eigenvectors are going to look like. And here's just one example of what you can choose. It's not the only one, but it's the one that we use in the paper. All right, so just a quick example, if that wasn't convincing, which isn't maybe that instructive, but you can see, following that formula, you can see how you do this for a three-state system, just given here. So yeah. All right, so first thing here I've got is just a theorem that says this is a stabilizer code. It's really not too difficult to see. First of all, for each C and C perp, we need to show that every one of these lies in the same eigenspace of each of these DCCs from SC. You'll notice that this is actually a stabilizer codes for SC perp, not SC, and so that's why we need to show what we do. And so if we want to do that, show that they're in the same eigenspace, you just apply it. You'll notice that what we end up here with, this omega to the tau c, that does not depend on the c prime. And really just give a little bit more details if you're interested. That's where this tau sub c is coming from. It does not depend on our c sub prime or our c prime, so we can see that this is indeed a stabilizer code. All right, so we're just gonna finish up with a little bit more terminology before I move on to kind of extending these things. So a stabilizer code can protect from any error in the set E if and only if for any two distinct code words. Really, orthogonal code words is what we want. And any two errors, we have that, well, after the errors, they remain orthogonal, and that they also have the same magnitude after applying these errors. And really, if you think back to that picture where I had the separate subsets, you know, since we're talking about quantum, you also often see this inverse, but you can just think of this as being E1 applied to phi C1, E2 applied to phi C2. You want to make sure you can still distinguish those. That's where this orthogonality condition comes in. And so with that, we'll just kind of finish up with some of these definitions that we're going to use throughout the rest of the talk. This first one, the conjugate errors, you can see exactly what that is. It's this E1 inverse E2 that we already see the significance of. And then this avoidance set and this difference set, really the reason we're giving them a name is because they're going to tie into that graph heuristic algorithm. And honestly, this difference set, when we noticed that that was showing up, that's when Rob and I kind of realized that there was this graph theory representation, because when I saw that, I was just like, well, that's just, you know, if I put this on a graph, that's just a Cayley graph, right? So kind of this symmetry here is really what kind of gave us that heuristic algorithm in the end. All right, and so putting these things in terms of this, what do we have so far with these reflexive stabilizer codes? You'll notice I kind of left something out that usually happens in CSS codes, which are kind of extending these things a little bit. And really, that's something that we need to do, because you can see here, well, I guess I'm getting ahead of myself. But let's just think about what these pieces mean. That first piece, the difference set intersects C is 0. Essentially, what's that saying? It's saying that if two of these errors occur, we're not going to get to another code word. So that's what that's telling us. And the avoidance set here, being a subset of C perp, essentially is telling us that none of these DAAs that would show up. If you look at here, this DAA is what we see in that avoidance set example. Those are how our codes are built. So we don't want those to show up inside C, otherwise we're not going to be able to correct them. And so that's really why we want that to be a subset of C perp. I'm going to skip through this proof, but what's the idea here? Again, just we're taking K logical qubits, where K is the dimension of C, in physical qubits. One thing that's not great about this, and is possibly the reason why no one's really looked too hard at these things, because it's not really crazy of a new application, right? But these things cannot correct all single qubit errors. So we think, Rob and I have discussed this, and we think this is maybe the reason why these things haven't been considered all that much. But we are going to make some extensions that get us a little bit more out of it. But first, an example which kind of just shows us how these things work again. Again, you can just take this back to the way I define them and see that this is exactly what you'd find. And what can we do? We can correct any single error from SC perp where SC perp is over here. All right, so what do we want to do? We want to extend these codes to give us a little bit more correction. We define two different extensions in the paper, but really we're just going to kind of focus on these flip error extensions. These are the ones that all of our examples later on are going to be sticking with. And really you can see essentially after protecting against those symmetric errors, we're going to protect against these flip errors and see what we can get out of that. It turns out we can that this is another stabilizer code, and we can correct more errors out of it, which is what this says. We'll see that with some examples later, which I think are more instructive. And another remark, I've been mentioning these CSS codes for those of you that are saying, okay, why should we care? You haven't done anything really that new. Well, we haven't yet. Again, that's going to be the next section, but you can really create an isomorphism from the errors that are occurring on these codes to the errors that you consider on CSS codes, and really show that these are equivalent to the CSS codes via this isomorphism. So you can see here, we're just taking the symmetric error to the flip error. That flip error, like I said, we're working with the flip error extension to the phase error, and you're going to get the exact same correction possibilities if you look at qubits. And really, theorem 422 here says exactly that. That's just a CSS code theorem, just rewritten in terms of our code here. And this 421 is there's similar types of theorems for qubits, and so this reproduces the similar qubit error correcting capabilities as well. All right. So I know there's lots of theory there, and I'm pushing a lot of things under the rug, but let's just look at some basic examples. So coming back to this Hamming code, this is another kind of classic CSS code, is taking the Hamming code and doing the same type of thing. All right, so if we take C1 to be the Hamming code and F2 to the 7, and take our C2 perp, sorry, our C2 to just be those two guys right there, then we're going to see that, okay, C2 perp is just all words of even Hamming weight. We can easily calculate what the code words are. I think it's important, if you're not following along, it's pretty easy to see how these code words are getting created. Essentially, you're just taking each of these code words in the Hamming code, and you're adding this guy here, right, the all ones. So 000s plus 111, and then similarly 0001011. If you add the all ones to that, you're going to see you get exactly what we have on the right hand side there. And so it's essentially just taking the dimension of our code, dividing it in half, because that's, you know, the dimension, because of the dimension of C2, and then it's going to allow us to correct some more errors. And according to those theorems, so what does that mean? Well, this means you can look at these weights. I don't think I actually said what the weights are. It's the minimum Hamming weight of a vector in that set. It's not the dimension or anything, so that's where that's coming from. And since this is the set of all even Hamming weight words, anything of weight 2, right, is not going to be in C1, as we can see. And so the weight of C2 perp less C1 is just 2, which gives us that 1, which means that we can correct any single qubit flip or phase error, but we cannot correct against those flip phase errors. So we're still not on to correcting anything. All right, so since we're doing qubits, we might as well look at something besides qubits, right? So let's look at F4. If we think back to what this idea is, what's the minimum size space that we could take a single 4-state qubit and encode it to get these corrections? Well, what do we have to do? Take our single qubit system. Well, if we're embedding it into a 1 qubit system, there's 6 errors we have to contend with. We go up to another one, got 6 more errors all the way up to n. And so then we end up with what, 6n plus 1 possible errors that we have to worry about, because obviously we want to correct or protect against no error happening, because that's kind of trivial. What does this mean? Well, for each of those 4 code words, we have 6n plus 1 errors we need to worry about, and that needs to be smaller than or equal to the size of our system. What does that mean? It means that if we want to take this 4-state system, we need at least 4 qubits to do that, to protect against these things. And we give an example here of a code, which we call the perfect code on F4, because it's similar to the perfect codes that you see with CSS codes. Basically, it hits that minimum. So we're taking F4, we're writing it kind of from this algebraic viewpoint as 0, 1, x plus 1, where x is 1, 0, and x plus 1 is 1, 1. And from this representation, you can start with this code word here, which we can see is 4 squared, so dimension 2 over F4. Take a subset, which I've highlighted here, and you can see what code words you get. And what we end up with is something that can correct any single flip or phase error. And this is over F4, so it's kind of an interesting example where these qubits come in. All right. So I'm going to go ahead and move on to talk about the graph heuristic algorithm, which I think is, like I said, the most exciting part of this, at least for Rob and I. Oh, that's not what I wanted. All right, so as I mentioned, that difference set, when I saw that, I thought Cayley graphs. And so that's what we're defining here. If you want to, you can think of Cayley graphs really as being a tool to provide a graph representation of a group action. Here we're only considering a special case where we're representing these things from an error set in a particular way, which we'll see. So these Cayley graphs, you can consider them. They don't have to be linear in general. In general, I think they're directed. You get different colors and all these types of things, but we're sticking to this very specific example. Linear undirected Cayley graphs, which we're going to call LUC graphs from here on out. And essentially, you just take a connecting set C, which we're going to take to be our coding. And then you just connect any 2 vertices if B minus A is in C. And you can see that how that ties into that difference set right away. And you get some of these pretty graphs. This one is on a 3-state system with n equals 2, with that connecting set 0, 0, 1, 1, and 2, 2. So you can see, right, 0, 0, that component that contains 0, 0 is exactly the connecting set. And then the other ones, right, so from 1, 0, you add 0, or you add 1, 1, you get to 2, 1. You add another 1, 1, you get to 0, 2, and that's how we're creating these things. So some really quick properties that you can notice, pretty trivial to recognize, is that you're going to have complete components. That really comes from the linearity condition. And from that, you can also see exactly how many components you're going to have. And as I just mentioned, you can see that the 0th component is exactly equal to C. So those are just some basic graph theory properties of these things. But what we want to do, we want to tie this into those theorems that we talked about previously. I meant to get rid of this theorem 4.02, so I recommend you just ignore that right now. There's some terminology there that I haven't defined. This is just a general theorem that you have for stabilizer codes that we're just kind of relying on for some of these results. But just translating the earlier theorem that we talked about, we can see that this flip extension RxC1C2 can correct any error from the set E, as long as this different set is a subset of these guys, the edges that are not in that graph. Right, and again, the idea is we want to make sure that those errors aren't going to take 0 and map it to a different code word. And you can also see the avoidance set here with C2 perp. We want that to be 0, or I think before we had it as a subset of 0, but in this case, it's I think it makes more sense to make it equality. And if you want to think about that on the graph, which we kind of basically ignore, and that's why there's some pretty interesting graph theory questions, I think you can take extensions here, is that these guys in the avoidance set essentially translate to loops on the graph. So we're thinking about simple graphs here, so not talking about loops, but there is some pretty interesting stuff you can add in, I think, if you want to dig into the graph theory aspects of it. All right, so what does this allow us to do, and why is it exciting? Why is it different than stuff that's been done previously? Well, this graph representation, what it allows us to do is really start with an error set. So if you think back to all those different systems that I mentioned earlier, the different companies are working on the superconducting qubits, trapped ions, whatever these things are. However they're building the system, it's reasonable to suspect that there's going to be inherent errors to that system that they're building. And the way that we think about quantum error correction right now is really from that classical point of view where you're like, oh, I care about bit flips, I care about phase flips, let's just tackle those, and then we'll see what types of errors we can get out of it. Well, here what we're doing is we're starting with the error set and trying to build an error correcting code from that error set. And I think that's one of the nice things about this representation that it gives us. So what are we going to do? We're going to start with that error set. We're going to build this avoidance graph. That avoidance graph again is just those basically given by that difference set. You can see these edges are given by AB such that DAB is in E2. That's exactly those that we got from the difference set. From there, you're going to take the complement because those are the things we're trying to avoid, hence the avoidance graph, and you're going to look for a subgraph that is one of these linear undirected Cayley graphs. Ideally, it'd be maximal, so you get as much error correction as you can out of it, but it doesn't have to be. You can still use this algorithm, but ideally, it'd be maximal. From there, and this part isn't really tied to the graph theory. That's kind of already been taken care of. It'd be interesting to see what you can say about the graph theory aspects that come into this next step. But again, you're looking for that subcode so that you get this avoidance set to not hit that perpendicular. So that, again, it has to do with those loops in the graph. And finally, in the end, you're like, okay, now I built a code that corrects from any single error from this set that I started with. So I've said it a few times, but really drive home what the key point here is. Here, instead of starting with the code and trying to figure out the errors we can correct, or kind of starting with that classical viewpoint of flips and phase errors, we're starting with an error set of possibly correlated errors and working backwards to find the error correcting code. All right, so let's just go through one example of this algorithm. So this is kind of contrived. We didn't take this from any application or any actual system. We were just trying to find one that had a nice enough picture that was big enough to be interesting, but small enough to be have a good visual with it. And so this is what we came up with these types of correlated errors here, where we've got basically what is this saying? If you look at the first one, that's saying, right, that we have a correlation between a flip error on the second qubit. I guess this is a qubit example actually. So a flip error on the second qubit and a phase error on the third qubit. And similarly for the rest of them, right? So that's a flip and a phase on the first one, and a flip on the third one, and a phase on the second one. And you can easily calculate that conjugate error set. And here, what I'm doing just for notation is basically taking, for instance, E1 bar, instead of being 100, that's going to be 011. So that's what the notation means. All right, so what does the avoidance graph look like? Well, it's just this guy here, because what's our difference set? Well, if you take any two of these things and subtract them, this is what you're going to get to. And you want to take the complement of that and find a Cayley graph that's a subset, one of these LUC graphs. And you can see those are the two that we had in that avoidance graph, so they're removed from here. So those gray edges are the ones that are possible to choose from. This is just one example of a LUC graph you can choose. And I've included that connecting set over there on the left-hand side. And you can see, again, you get some pretty cool symmetry out of this thing, and you, again, have the complete connected components. From there, we're going to find a subset. And we don't really have a great strategy for this part yet, but you'll notice that we can find this subset here such that this perpendicular intersect the avoidance set is the empty set. How do I know that? I didn't tell you what the perpendicular is. Well, what's the avoidance set? I think this does a good job of showing us what that is. I've highlighted that. These are the DAAs that happen in that conjugate error set. And so really, all we need to do to check that this is a true statement is to see if either of those two things is perpendicular to C1. And they're not, so we have exactly what we need. And we can conclude that this extended reflexive stabilizer code can correct any single error from that correlated error set up there. So there's our graph heuristic algorithm as an example. And I think that's really all I've got for you besides a list of future work and open problems. So this is really a new area, so lots of open questions. Theory ones are the ones that I'm maybe less capable of solving, so there's plenty of them. I listed a few general properties there of those LUC graphs. I'd be interested to know what are other properties of them. I'd also be interested in what can be said about connecting these things to these error sets. So what properties on that error set guarantee the existence of these sub-LUC graphs to that complement of the avoidance graph to utilize there? What properties on two different error sets guarantee the same LUC graph? So, you know, would we be able to tell just by looking at two different error sets that we're going to be able to take the same error correcting code and be able to correct those different error sets? That'd be something pretty interesting. And then maybe something that might be in my wheelhouse and I think is pretty exciting is which of these LUC graphs exhibit state transfer using these quantum random walks, either discrete or continuous, right? This is a method for writing quantum algorithms. And then somehow, you know, my hope would be that the LUC graphs that we end up with are somehow tied to the actual architecture that you might be end up using. And so then these algorithms would make sense to talk about actually, you know, trying to get state transfer from one state to another and actually have an algorithm that can compute something. So I think if this last question, I think there's lots of positives if you can get answers to that. Other things just in general about reflexive stabilizer codes, and Rob and I have been thinking about this a little bit, but we haven't really delved into it yet. You know, like I said, he's running that math department at his college, so it's kind of a start these things in the summer and see what we can do in a year. So can we extend these things at all any further? Can we get some type of fault tolerant computation involved in these extended reflexive stabilizer codes, or can we implement C-naught gates and incorporate those into the graph representation? I think these would be pretty interesting questions. Maybe more interesting and more to the point of kind of the story I've been trying to tell here is how can we apply these to industry? So what are the correlated errors similar to what we talked about in that last example on these architectures that are that exist? What types of correlated errors are they having problems with? So this is more of like a, you know, if you know, please tell me, because it's kind of a lit search thing, I think. But also, you know, yeah, I have to think about different types of codes that you're trying to do error correction on. Like A lot of these superconducting qubit machines, their algorithms rely on surface codes, and I know Rob is interested in that. He's already kind of started thinking about it, and if anyone else wants to jump in on that, I know we both enjoy collaborators. And that kind of gets into what I said there. I think I already said it. Given error sets from common architectures, can we create reflexive stabilizer codes which correct those errors? Which again is kind of the big point that I've been trying to get at here. So I guess in conclusion, we've got some codes that look similar to CSS codes, but they give us a new viewpoint. And we've got plenty of open questions. Some of these might be suited for undergraduates, some maybe for graduate students or beyond. But I think there's a lot of interesting things going on here. So thanks everyone for coming. Thanks for your attention. If you want to see more details about the actual math that's involved here, you can check out this paper on arXiv. We've submitted it for publication, but still in that process. Other background reading, you can see these Calder Bank papers. These are basically on the qubit codes, kind of the introduction stuff. And then these two nil papers get more into the qubit error correction. And that's where you can find a lot of the background, those theorems that I kind of glossed over there. And yeah, so thanks again. Any questions?
All right, so if there's no questions, let's thank Duncan for speaking to us today. Enjoyed the talk.
Oh, Steve Finner, you had your hand up?
I was trying to find a applause emoji. I hit the wrong button.
Oh, okay. Well, you got my attention. I appreciate it.
Yeah. So, yeah. Anyway.
Nice talk, Duncan. Thank you.
Yeah, no problem. Kind of just get up here and talk. Sometimes over Zoom, I never know what's going on.